Okay, so it's a pleasure to have Christopher Hughes from University of York, and he's going to speak on a random matrix model for Graham's law. Please, Chris.
Thank you very much. So, and thank you very much for the invite to talk here this, well, I want to say this evening, but who knows? Now everything is worldwide. Yes, I'm going to talk about random matrix model for Graham's law. This is mainly based on work of my former PhD student, Katalin Hanger, and this formed the majority of his thesis, and then that was a couple of years ago, and then some work's been going on since then. I'm going to start with a song, which I actually won't sing for you, but it sort of sets the tone. So where are the zeros of zeta of S? GFB Riemann has made a good guess. They're all on the critical line, saith he, and their densities 1/2 pi log t. And this talk is all about the zeros of zeta in some sense, and how well behaved they are. So I want to remind us of things that I'm sure we are all reasonably familiar with. So the Riemann zeta function satisfies a functional equation that maps S into 1 minus S of this form that I've got up on the screen. And if we put S to be on the critical line, 1/2 plus IT, then you can see that the sort of that transformation function, the chi function, has got magnitude 1. And so we can write it like this: e to the minus 2i times a real function theta of t. And the 2 and the minus are convention. And what this enables us to do is, so if I don't know, can you see my mouse? I hope you can. So I'm at the top equation. You've got zeta of S is, so if I write this as e to the minus 2i theta of t, zeta 1 minus S, and then I sort of take one of those e to the minuses and pull it over onto the other side, I've then got a function that is, if you think about it, is an even real function. So I've sort of defined Hardy's function, this z of t, as e to the I theta of t, zeta 1/2 plus it. It's real and it's even. And you can check that from the functional equation. And this means finding zeros becomes much simpler, because you can plot a real function and find where it changes sign. And where that happens, you have a 0, right? The intermediate value theorem comes to your rescue and you've got a 0. And this is actually how they do it. So if you try to plot the Riemann zeta function as a complex function, which I've actually got on my t-shirt, hard to see, but it's finding, it'd be much harder to verify a 0 that way. Here you can rigorously say, yep, definitely positive here, definitely negative here. I've got a 0 in between them. And this is how we numerically calculate zeros. Now, another thing that I'm sure is very well known amongst all of us is that as you go higher up the critical line, these zeros become more dense. They squish together. There's more of them. And you can see that when you do look at the counting function for the zeros. So n of t is going to count the number of zeros between up to height t on the critical line. And this was in Riemann's original 1859 paper, minus proofs. You can write that, this n of t, this counting function, you can write it as a smooth term, which I call n bar of t here, plus an error, s of t. And n bar of t, if you work your way through the mathematics, is 1/pi theta of t. So that was the same theta that we saw back here. It's exactly this same function turns up in the counting function. +1, which is there for reasons I don't want to get into. And then you can do a asymptotic expansion, Stirling's formula. This has got a bunch of gamma functions and stuff in it. Again, you can see that it's all of these gamma functions here. If you take their imaginary parts for large t, then you have that the counting function is t upon 2 pi log t upon 2 pi e. That was the bit that you had in the poem at the start, plus 7/8, plus an explicit, this is a smooth thing. So I've got an explicit asymptotic expansion for it. And the error to this, counting functions are discontinuous jiggity jaggedy thing. The error is this s of t, and that's small. Who was it? Von Koch, I think, showed that it was big O of log t back in turn of the century, 1901, something like that. So it's the correction term. It's kind of where all the interesting meat happens normally. But it's considerably smaller, right? Log of t is considerably smaller than t log t. And log of t is, in fact, an overestimate, and you can do even better than that. We believe that is actually not quite the truth, and s is truly smaller. And I'm not going to talk about that at all, even though I said that's kind of where all the interesting stuff happens. For this talk, we're going to be concentrating more on the behavior of the smooth term, n of t. And I'll come on to that when I explain Graham's law in a minute. But let me just show that this really is a good approximation. So what I've got here is the genuine counting function for the zeros of zeta. So the first one is 14.13 something. The second one is at 21 something. And so the function sort of jumps up by 1 and jumps up by 1 and jumps up by 1. Every time you see a 0, it increases by 1. But it's a staircase function. It's discontinuous. If I overlay the smooth term on top of that, you can see, yeah, that's doing really, really well at approximating the counting function. Now, the real n of t jumps 1 at every time it hits a 0 of zeta. I mean, that's its definition. But if you wanted to get good ideas for where the zeros are, you want to sort of bound them in. And then what you might be tempted to do is say, well, actually, this is this smooth term, which is so much easier to work with. If I find where it goes, where does it equal 100 and where does it equal 101? Well, that's much easier to calculate that. And somewhere between that, I would sort of be, it'll be a reasonably good guess. You might see the 101st 0. And that's exactly what happens. So these red dots are where the smooth term, that n bar of t, equals 1 or 2 or 3, etc. And you can see that they bracket the genuine zeros of zeta, which are tremendously hard to calculate. So formally, I'm going to define the kth Graham point to be where theta, the function we saw at the start, of the values where that equals pi times k. So this would be the 0th Graham point, the 1st Graham point, etc. Why is it pi times k? Well, if you look over here, I've divided by pi when I did the counting function. And in 1903, Graham calculated the first 15 zeros, and he made this observation that they interlace with where this sort of n bar of t equaling an integer interlaces with where z of t equals 0. And it was 1925 that Hutchinson actually coined the term Graham's law, And he wrote this. He said that so referring back to the 1903 paper of Graham, he said Graham calculated the first 15 roots and called attention to the fact that they separate each other. The roots of zeros and the Graham points separate each other. And I will refer to this property of the roots as Graham's law. And Graham expressed a belief that this law is not a general one. And it's true, it's not. So you can find instances where the Graham points don't separate the zeros of zeta. And I've given an early example here. This isn't the first. I think this is the third example where it happens. So I've got an interval, a Graham interval, so one Graham point, another Graham point, that contains two zeros. And then I've got a Graham interval, so Graham point to the next Graham point that contains no zeros. And then things head back to being normal. So it's a good rule, but it's not always true. How often is it true for? And answering that question is the purpose of this talk. So we've got a law that in every Graham interval, so that's the interval between two consecutive Graham points, I expect to see exactly 1 0 of the zeta function. It's not always true. How often is it true for? So that's what we're going to try to answer. So we can do some statistics. So for the first 100 billion zeros, 100 billion Graham intervals, then we can see that it's true for 71.7% of the time. Do we have is there exactly 1 0 in a Graham interval? Now, this data is, so we got these zeros from David Platt in Bristol. He calculated 103 billion zeros, and very kindly, to accuracy to 100 binary digits, and very kindly let me have a copy of them. It takes 1.3 terabytes. So if I was allowed to be in my office, which I'm not at the moment, if I was allowed to be in my office, I would have an external hard drive that's a 2 terabyte hard drive full of Riemann zeros. And that's what we used here. That's what Catalin, my PhD student, used. I had very little to do with the numerical calculations on the programming side. And so he analyzed these and came up with this data here, which beats what was previously in the literature. I think that went up to 1.5 times 10 to the 9 was the previous numbers. Things don't change much. But anyway, so we analyzed all the zeros that were available to us for the proportion where you've got a Graham interval with no zeros in it, a Graham interval with 1 0 in it, etc. And just to give us something concrete to look at during this talk, I'm going to be mainly concentrating on how likely is it that a randomly chosen Graham interval will have exactly 1 0 in it. Now, there's a bunch of theoretical work that has already been done. Tim Trudgian's doing a lot of stuff on this, and various other people too. But there are many questions left unanswered. So I want to sort of motivate the way we're going to be attacking this problem. So recall Hardy's functions. This is the real function that was of the same size of the Riemann zeta function. This, so you can find the sign changes. So that z of t is e to the I theta of t, zeta a half plus it. Now then, remember the definition that a Graham point is when, so the kth Graham point is the value where theta of g of k is equal to k times pi. So it's pi times an integer is what you get at a Graham point. Now, so e to the I pi times integer Oh, well, that's plus or minus 1. Z is real. So that means that the Riemann zeta function is a real function at the gram point. So normally it's complex, right? Again, my t-shirt, right? It wraps around. But at the gram points, it becomes a real function. It has no imaginary component. And we can see this in the following animation. So we have a gram point, another gram point. That just gets ourselves going. There we go. So 0, gram point, 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 0, and it goes on. Now, the other observation that you might make from this is that looks a bit odd, doesn't it? Because all the times that we've seen it, it's when the zeta function is real, it's either going through the origin, that's a 0 of the Riemann zeta function, that's what number theorists really are interested in, or when it's crossing the real axis, it's doing that in the positive side, the positive real axis. And again, that's another manifestation, a slightly different manifestation of Graham's law. If I just go back up a slide. So remember, the gram points are where this is an integer multiple of pi. So e to the I theta from consecutive gram points is going to go +1, -1, +1, -1. Now z changes sign. So if you've got a 0 inside a gram interval, then z would have gone from positive to negative. So that means at the edge of that interval, it's gone from positive to negative, but also this has gone from negative to positive. And so they cancel out. So if Graham's law was always true, which it's not, then this zeta wouldn't just be real, it would be real and positive at the gram points. That's another way of thinking about it. Now, it's slightly different. We're saying Graham's law is there's exactly 1 0 in an interval. And so you could have, say, 3 zeros in an interval, and you would still keep the same sign for zeta at the edges. So I'm not saying that's an equivalent definition, but it illustrates why, when we do this graph, that because there's frequently 1 0 in there, this frequently goes through, when zeta is real, it's often real and positive. There's another way of thinking about things. Okay, let us move on. So I want to move on to the next bit of the story, which is random matrix theory. And I'm not expecting us all to know much about random matrix theory, and I'm not actually going to tell us much about it, but I do want to sort of introduce it. So the idea is that we've got these zeros of zeta, and they're clustering up, they're getting squished together. So we stretch them, we unfold them, we pull them apart, we rescale them, so that on average, the distance between them is 1. So that's not saying that we stretch them so that the distance is always 1. You've still got that fluctuation going on, but their mean is comparable. And that's what's going on here. So this is, I forget where I plotted these, but some high up in the critical strip, but I've stretched them out so that the average gap between them, or roughly the average gap between them, is 1. And if you did a bigger average, it would converge to 1. So that's what's going on here. You kind of multiply each 0 by its local density. And the conjecture is that these scaled zeros statistically look very much like scaled eigenangles of unitary matrices chosen with Haar measure. So the matrix group, unitary matrix form a group. It's a compact classical group. It has a Haar measure, which is the unique measure that's invariant under action by that group. And I can, left and right Haar measure are the same because it's compact, uniqueness because it's compact. These are nice things, well studied. So Weil looked at them in 25, something like that. And this conjecture that the zeros of zeta look like eigenangles of Haar distributed random unitary matrices has been well studied, going all the way back to Hugh Montgomery in 1973 had a conversation with Dyson where they realized this connection. There's a ton of people involved. I've listed a few, and there really are many others. These are sort of the historic figures involved in this. And I kind of don't want to justify it. I just want to give you some pictures. So first of all, if I take a unitary matrix, that's what I've got on the side, and I plot its eigenangles, well, they all lie on the unit circle, right? I mean, that's a property of unitary matrices. But if I choose it with Haar measure, it's got some structure to it, and that manifests itself in the distribution of the eigenvalues. And it's different from just throwing points down independently at random on the unit circle. And I want to, I'm not going to talk much about the distribution of the eigenvalues. I will in a minute, but not much. But if you just look at this picture, you can see that this picture looks very different from this picture. So this is where I've just thrown points randomly down, and this is where I've actually picked the matrix and found its eigenvalues. Got big gaps, I've got clusterings over here, much more spread out, much more spaced on the left-hand side. Excuse me. Now, if I now take some zeros of zeta at approximately the right height, so about 10 to the 22nd zero should roughly correspond to 46 by 46 matrices. I'll explain why later. You can now see that these pictures look much closer. You can look at these and go, yeah, maybe there's something going on. And I can do better. Another proof by pictures. So if I look at the nearest neighbor spacing between the zeros of zeta, and I sort of empirically work out, well, if I've got a zero at one point, how likely is it there'll be a zero 0.5, a scaled zero 0.5 away? And if you sort of bin them into histograms, this is what Andrew Odlyzko did back in the 1980s, then you have these black dots that you can see on the graph. And if you ask the equivalent question for random unitary matrices, then you get the smooth curve that you can see. And the fit is incredibly good. So proof by pictures. If I ask the same question for points placed randomly around a unit circle, then my smooth curve would look remarkably different. It would look like the exponential curve, a Poisson distribution. So you can really see something is going on here. And then, yeah, so Montgomery was the first person. So we didn't actually calculate the nearest neighbor spacing. It's a difficult beast to get your hands on. Instead, what we did was calculate something called the pair correlation function. So rather than saying I fix a zero and I look at the next zero, the consecutive zero, it's much easier to say, well, I'll look at the gaps between zeros, but they don't have to be consecutive. And that's what's happening here, is I'm looking at scaled zeros, but I'm not insisting that they are consecutive zeros. So this is all zeros, all of the gaps. Now, if f decays rapidly, obviously this is going to pick up only those zeros, this is morally like a double sum, and it picks up only those zeros that are close to, so gamma primed, that are close to gamma, because f is decaying. So the further away they go, the bigger this is, and has much less weight to that sum. But the analysis is much easier to do it like this. And this is the kicker. The question we want to ask is jolly hard to solve analytically. So we have to manipulate it into a question that we can ask and solve. And it introduces combinatorial complexity. And what Montgomery did was he found, well, if f has some restrictions on the support of its Fourier transform, then this sum, pair correlation, ends up as equal to the integral of f times this kernel, this sine kernel here. And we'll see this kernel again later in the talk. I'll just explain this. Delta function is very easy to explain. This is, if you look at the double sum, I've got gamma primed. Well, if gamma equals gamma primed, which will happen for every single zero, if I'm summing over a pair of zeros, I just pick, the billionth zero in one sum and the billionth zero in the other. Well, the distance between them is obviously 0. So that explains why you always pick up f0, if you like, with the appropriate weight. Okay. Another proof by pictures that this thing makes sense. So I've plotted here, I've ignored the delta function, and I've plotted 1 minus sine pi x over pi x all squared. That was the analytic answer. And the dots are the empirical pair correlation for the Riemann zeta function around the 10 to the 20th zero. And this data, as I said, comes from Andrew Edlisco. So we believe that random matrix theory is a good model for the zeros of the Riemann zeta function. And so Fujii conjectured that maybe the proportion of Gram intervals that contain exactly 1 0 is going to converge to the probability that a n by n matrix, if I take a random interval of size, scaled size 1, which means real size 2 pi divided by n, then if I find the probability that that contains exactly 1 eigenvalue, then those two might be equal, right? I mean, this is the statistics saying that the two are statistically similar. So that was his conjecture. So just before I go on, so why is this 2 pi over n the same as a scaled interval of size 1? Well, let's think about what the scaling would be for a matrix. So if I've got an n by n unitary matrix, I've got n eigenvalues. They all lie on the unit circle. How big is the unit circle? Well, it's 2 pi big in angle size. And so I've got n dots to put around 2 pi. So their average gap between them is going to be 2 pi divided by n. It really is that simple. So this probability on the random matrix side is denoted by E11. So this one says this is the number of zeros I want. And this one denotes the length of the interval. So in scaled world, this interval has got length 1. Now, in his paper, Fujii said it's roughly 0.74. It's not quite right. He actually got that number from doing a series expansion of E1, S for small s, and took the first, I can't remember, 3 terms of the Taylor expansion around s equals 0, and then plugged s equals 1 in. So that's not quite right, but you can work this out exactly, and you get that it equals 0.6614, blah, 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 blah. So you can actually calculate that. Now, if you compare that with data, so if we looked at the first 100 billion Gram intervals, the statistics there was this should be roughly 0.7135. So, in the right ballpark. I didn't like this conjecture. I don't think it quite captured what's going on. And the reason I didn't like it is that what the conjecture did was it just threw a random interval down anywhere, plump, and it said, how likely is it that a 0, exactly 1 0, lies in this randomly dropped interval? But Gram points are special, right? They're where the counting function is an integer. They're where the zeta function is real, right? They're not just randomly chosen things. They're special. And I want to illustrate that with a silly little example, but it sort of demonstrates what I mean. So let's say we've got a bunch of integers, 1, 2, 3, 4, 5, 6, 7, 8, 9. And between each integer, I randomly drop a point, plop. So, and I put exactly 1 point between integers. There'll be exactly 1 anywhere between 1 and 2, another point anywhere between 2 and 3, another point anywhere between 3 and 4, etc. So that's what's going on up here, just mathematizing that. Now, if I pretend that the integers are my gram points, and then a randomly chosen gram interval will always, always, always contain exactly 1 point, because that's how I designed it. I dropped a point between 1 and 2. I dropped a point between 2 and 3. But if I just dropped a random interval of size 1 somewhere down here, plop, it could, and probably will, have straddle 2 gram points. And it's not impossible that my randomly, when I put my points down, that they were outside. So this one was too far to the left on that side. This one was too far to the right on this side, and it misses my randomly chosen interval. And if you work the way through, you get a probability of a random interval having no points inside it is 1/6, despite the fact that on the gram intervals, it's always happens. So now that's a toy model, but it demonstrates that one does need to be careful. And the Fujii conjecture just throws a point anywhere down, and it makes no attempt to distinguish the fact it needs to be a random gram interval thrown down. So we need another way to think about gram points. And I just before I come on to that bit, in order to think about that, I need to create very quickly a random matrix model for the Riemann zeta function, not for its zeros, but for the zeta function. And famously, this was done by John Keating and Nina Snaith back in, well, 1998, roughly, that sort of era. So a couple of decades ago. And they said it's the characteristic polynomial of a random unitary matrix. That's the right thing to model the distribution of the values of the zeta function itself. And they said that at finite height, you want to collect your matrix size n should be log t upon 2 pi. We've kind of seen this before. This is equating densities. Remember when we scaled the zeros, we scaled them by their mean density, 1 upon 2 pi log t upon 2 pi. And we scaled the eigenvalues by their mean density, n over 2 pi. You equate the two and you get that equation at the bottom. Bit of maths just to verify that it kind of sort of works. So Selberg back in the 1940s, 1948, showed that the log of the absolute value of zeta has a central limit theorem type result. And Keating and Snaith, when they were looking at the characteristic polynomial, showed that that has an equivalent central limit theorem. It converges to a normal distribution. And again, n is log t, so the scaling fits. So both of these converge to a normal distribution, proof by pictures again. So the black is the Gaussian curve. Theorem says that green, which is random matrix theory, characteristic polynomial, and red is the empirical distribution for the Riemann zeta function. For large T, large N, they will theorem converge to the black curve. But if you look at this picture, you can see, it's doing so much better than that. They're practically on top of each other. So no proof or explanation or anything, proof by pictures. Random matrix theory, the characteristic polynomial of a random unitary matrix, is a good model for the distribution of values of the Riemann zeta function. So I want a random matrix model for gram points. So remember that at the start I said that a gram point is where the zeta, a half plus I G, is real. Okay, so one of our alternative ways of thinking about gram points is it's the points where zeta is real. I guess real and non-zero. So I asked myself, well, what values of theta make the characteristic polynomial real? Well, that's all right. I can do a little bit of analysis here, a little bit of algebra. So I've got the characteristic polynomial. It's written in this way. So lambda is going to be my eigenvalue. Theta is my input. It's a slightly unusual way of writing things, but this is just how we did it. And then if you kind of pull stuff out in order to make this term here real, I can turn this, I pull out half of these arguments outside. You can say I'm going to end up with a sine function. Okay, this is looking like a sine function. And what do you pull out? Well, you've got to pull out a half of e to the I lambda j for each j. So that's these terms here, one for each j. And I've got to pull out an e to the I, e to the minus I theta n. So I pull half of that out, but I've got one of those for every term in my product. There's n things in my product, so there's the n there. And then there's a factor of I that comes out in order to turn this into a, well, 2i in order to turn this into a sine. So you can do that and you see, right, 2 to the n, I'm going to ignore you, you're real. Sine of a half lambda j minus theta, well, that's real, and that's going to vanish when theta equals an eigenvalue. So that's kind of like the zeros of zeta. So, but it's real. So what makes this is my complex term. What makes this real? Well, I need this to be a multiple of pi. And so my gram points will be, well, what values of theta make this a multiple of pi? And you can easily see, you multiply through by 2, divide by n, and there's going to be n equidistributed points around the unit circle that make this the sort of the random matrix gram points, where we've defined them to be where the characteristic polynomial is real. And so I've written them up here. Now they depend on the arithmetic average of the eigenvalues, which makes it a bit difficult to work with. But one feature of random unitary matrices is chosen with Haar measure is that they're chosen with Haar measure, which was defined as the unique measure that's invariant under action of the group. So what does multiplying by a unitary matrix mean? Well, it's morally speaking a rotation. So I can take any matrix and I can rotate it, and the measure of that matrix, I'm roughly speaking here, I know these are continuous measures things, but the measure is unchanged by rotation. So I can rotate it so that the determinant is 0. In other words, these eigenvalues I can rotate so that it's they are 0. And then that gives me a special unitary matrix. And that's what we're going to do. So if you choose a matrix from the SUN group, then the argument is 0, mod 2 pi. And your gram intervals are evenly spaced, and they don't depend upon the eigenvalues. Now, I've sort of taken that bit of messiness out, but I've made it worse by insisting I'm in the SUN group rather than in the UN group. But the conjecture now should be not throw a point randomly down on a unitary matrix, but it should be what probability is there for an eigenvalue lying in one of these random matrix gram intervals. And that's the task that we need to answer. So I've written out the density. I'm going to do a little bit. I'm not expecting people to know much random matrix theory at all. So I've got some equations. There's not enough information here to follow as you go through, but I sort of want to point, why was this difficult? So the unitary group, the Haar measure for unitary group is well known and well studied. This was done by Weil, and it's this van der Monde determinant. And it's a beautiful measure because you can turn it into what's known as a determinantal point process. You can write this as some determinant with a nice kernel and everything works fine. Now, the density for SUN matrices with Haar measure is this. So you've got all your nice bits over here. This looks very similar. I've got a van der Monde determinant. But then I had to kind of rotate things round so that my nth eigenvalue is sort of determined in order to make the matrix have determinant 1. So I don't have free choice on n eigenvalues. I've got free choice on n minus 1 eigenvalues. And then the last one is fixed, is determined by those. And that's what's going on here. And this measure doesn't have a determinantal point process. We can actually show that. So it doesn't have all the nice things that those who study random matrix theory, just their go-to toolbox is putting things into determinantal form. We can't do that here. So we had to go back to basics. And again, it's a bit of a mess, but let me try to explain what's going on. So we try, what we're after, what we want is this term, EKJ, where this is the probability that there are exactly k eigenvalues in some interval j. That's what we want. And as I said right at the start, with things like the nearest neighbor spacing, it's really messy to calculate these. So what we do is we turn them into a generating function. So curly E is sort of the generating function for the probabilities that we want. And we turn it into this form of generating function. And then if you do a little bit of thought, you can actually see that this is equal to this product here, where you average over the unitary group or the special unitary group, depending on what calculation you're doing. And then you can expand out the brackets and you get a sum of z to the n over n factorial times the integral of something known as the n-level density. And what that is, that's if you think about having a probability density, this probability density here, this is the distribution for having eigenvalues at theta 1, theta 2, theta 3, all the way around to theta n. The n-level density is you say, okay, what's the probability density of having eigenvalues at theta 1 and theta 2, and I don't care about the rest, integrate everything else out. And that's what's going on. So you say, I'm going to, so R2 would be fixing 2 values to have an eigenvalue at, and then you don't care about the rest. You integrate everything else out. So that's what's going on over there. And a bit of thought shows that these are equalities, and they're true for everything. Now, in the unitary case, life is nice because I can take that generating function and write it as a determinant. That's not that hard to calculate. Okay, so this is sort of standard stuff in random matrix theory. Don't worry if this isn't an area. Just let me tell you, it's nice in the unitary world. And you want to find the probability of having exactly one eigenvalue in an interval of length 1, then that's going to be the derivative of this generating function evaluated at z equals minus 1. So if I just show you back there, so z equals minus, if you differentiate this, but z equals minus 1, then that kills off all the higher things and the derivative just leaves me E1, j. And then you put j to be an interval of length 1, or length 2 pi over n. Sorry, I'm scaling. So the unscaled interval of length 2 pi over n, which is a scaled interval of length 1. And you work your way through the maths, and you do a bit of calculation, and you get the answer 0.6614, blah, 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 blah. Now then, it's not so nice for the SUN case. There is no determinantal form. We can't do that calculation. So we have to go back to the second line we've got down here, where it's a massive sum of these n-level densities. Harumph. So what we want to calculate is this sum of these n-level densities. But what we were able to show, and is not remotely obvious from here, but if you work through the mathematics, you can show that the n-level densities in the SUN case are equal to the n-level densities in the UN case. Oh, I can deal with those. plus some correction term that's not too big. That's the heart of the maths, and you're missing it all, but trust me. So this is the n equals 1 case. So this flat line is the unitary case, and then there's some small correction to it in the SUN case. They're not the same, but it's similar. It's roughly the same. And this correction is of size 1 upon n, different. And in the n equals 2 case, this is why I didn't want to give you too much maths. The correction term is, I mean, this is nice, but you can see it's going to get really ugly. But you can do these calculations. It's not helpful to see it, but the picture actually isn't terribly clear either. But you can sort of see it's roughly the same as the unitary case, but not quite. And so that's what we were able to show. So all of these n-level densities are the unitary n-level densities plus some small correction. So if I want to calculate, I'm going to plug in a gram interval, right? This is what I'm after. I want the probability of exactly one eigenvalue in a gram interval. So that involves doing calculations in SUN, and I can do the calculations in UN, which I can do because the unitary case is so much nicer. It's got this nice form that I can work with, plus these small corrections. And so let me just go back a few slides to show where I'm going with this. So I want to calculate this beast and do some differentiation. I can write this in terms of these are integrals of the n-level density, and it's a sum, and I can write each integral of an n-level density as the thing on the unitary case plus an error. So if I do this sum here for everything on the unitary case, I'm going to be left with stuff I know. So all I have to do is do the sum on the error terms, the bits that I don't know, these x's. So one can show that the integral over the correction for x1 is 0. I mean, the picture sort of says that's right. Below the axis is about the same as above the axis. And you can calculate the integral on that much more messy one for little n equals 2. And you end up with a correction term of size 1 upon n, some constant over pi squared. And this constant is equal to roughly 1. Plus an error of size big O n 1 upon n cubed. And the others are similar. In fact, so we can show that all of them are big O 1 upon n, but their constants are much smaller than roughly 1 upon pi squared. And so that's what we were able to achieve. And so putting all of this together, well, I started out by saying I was a little bit disappointed with the Fuji thing because it hadn't really grasped what a gram interval is. It just said, oh, just chuck any old interval down and work out the probability of getting an eigenvalue in it. Well, he wasn't wrong, because in the large n limit, all of these 1 over n terms disappear. But it's much better for finite n, far better agreement with data. So you've got your n equals infinity limit, but around the 100 billionth gram interval, well, that equates to roughly n equals 22-ish size of matrix, and you get a correction term of size 0. Not far, it makes a significant difference. 0.662 goes up to 0.709. And so if I look at the actual data, you can see that the SUN approximation is far better than the UN approximation, even though as you go higher and higher and higher up the critical line, we know that these proportions are going to converge as n tends to infinity. At finite n, this is a much better approximation. Yeah, so in conclusion, what have we done in this talk? So why look at gram points? Because they're dead easy to calculate. And they're very, very good at telling you where you expect roughly to find zeros. That's because the smooth part of the counting function is just so darn good at modeling the true counting function with its wiggles. We know that the zeros of zeta are modeled by random matrix theory. I mean, that's a tremendous industry going on. And we can calculate the probability that there's exactly one eigenvalue in a randomly chosen interval of length 1. But doing so takes no account that you're trying to do gram interval calculations. So what we did is we created a new, better random matrix model for gram intervals, which involved developing the theory of random matrix theory on the SUN group, which is a much less studied area in random matrix theory, because it's not as nice. It doesn't have the same structure, but it's, you know, it's a perfectly decent group and it deserves a bit of study. So that's what we did. And it converges to the unitary case for very large n, but at finite n, the fit with the zeta data is much better. Now, I started with a poem. I think I'm going to finish with a poem. This is, I forget who actually originally wrote this song, but I'm the one who changed the last line. It goes, "There's a moral to draw from this sad tale of woe, which every young genius among you should know. If you tackle a problem and seem to get stuck, just use RMT and you'll have better luck." Thank you very much.
Thank you, Chris, for the math and poems. I'll open for questions now.
So I have a question. Is it possible that a gram point can be an imaginary part of a Riemann zeta zero?
Yeah, that's a good question. So could it be possible that the zeta zero and the gram points lie up? We don't know, but almost certainly not. It's highly, highly unlikely. But yes, that is something one needs to be aware of.
Hi, Chris. I thought it was a very nice talk. Is it possible to kind of reverse engineer what you did a bit? So you started off with quite a natural problem about the spacing of zeros between the gram points, and you did some calculations, and it transpired in the end that in the limit, the answer was the same as the kind of naive conjecture. So could you kind of contrive, but not too much contrive, a different kind of problem so that looking at the gram points would give you a genuinely different answer in the large M limit?
That's a nice question. I haven't thought of it. We know that, so on the local statistics, we know that all the corrections are big O1 upon n. I don't know. That's a nice, that would be nice. I mean, it would be nice to be able to come up with a proper, decent problem where the answer does require SUN even in the limit. So so thank you very much for that. And I'm ashamed to say I can't off the top of my head construct such a thing. But it's
I don't know whether it's reasonable to expect something or not, but you seem to have a nice kind of model now for what the ground points correspond to on the random matrix side. So it seems you at least have the tools to kind of start thinking about whether there could be something or not.
Yeah. So what I'm trying to do at the moment is the proof is it's messy. There should be I think there is a neater way of doing the SUN analysis. I mean, it's going to be ugly because you lack the determinantal point process stuff. But some of the other kind of general results might be able to come in and get that. Sorry, where's my mind going with this? Yeah, so at the moment, okay, so what I'm trying to do at the moment is find neater ways of developing the theory in SUN matrices. The answer is yes, I think we do have the right model for what random matrix ground points are. So yeah, the challenge is going to be find a decent question in that model where you genuinely end up getting different results. Yes, that is an excellent challenge. Thank you.
And any other questions?
I also have a question.
Sure.
So I was wondering, when you define your characteristic polynomial lambda un, so is that going to be positive at the random matrix ground points as well, just like the zeta function?
Yeah. Let me go back to the screen. It's not working. There we go. So the characteristic polynomial is here. I'm so sorry. Doing that has made your question fall out of my head. What was your question again, please?
Yeah, so when you look at the corresponding ground points in the random matrix Euro case, this characteristic polynomial, is that also going to be positive valued? So it's going to be real?
Ah, right. It will be predominantly either positive or negative. There's a subtlety here. So, okay, I understand the question now. So like with zeta, it was always positive. Here, if no, wrong way. It's down here, isn't it? When you plug in the had we chosen to not add the +1 to the theta of t, then the ground points would be predominantly negative, right? You could imagine flipping the sign of Hardy's function, and so then rather than being predominantly positive when you go through a ground point, it would be predominantly oh, that's not true. That's not true for zeta. That's just Z. I forget. My memory is it can, for a particular matrix, it's predominantly one, either plus or minus. But when you average over the group, it switched sides. But I'm struggling to remember the reasoning now. Yeah, I have thought of that and I'm afraid I can't reconstruct the argument. But you have so if you pick a particular matrix, then it has a bias. Did it? Yeah, I can't reconstruct the argument, I'm afraid. Sorry.
That's okay. Thank you.
There are more questions? Okay, maybe. If not, I have one actually. I was thinking about was the I mean I wonder what happened when you change between UN and SUN. Was this a choice? I mean, could you have worked with UN and somehow
Yes.
keep track of the statistics of the average of the eigenvalues?
Yes, you could have done, but what would have happened is that your Gram intervals then rotate around with the determinant. So in fact, we started with just working with UN, but it kind of met. But then your sort of local statistics suddenly actually needed to know all the eigenvalues at the same point, and that kind of it messes it up in the same way. So in fact, if you take a unitary matrix and you say, right, I'm going to fix you so the Gram intervals are in their right place, then doing that, when you plug it into the characteristic polynomial or into the densities, by rotation invariance, you actually get forced back into SUN, just rotated around by something. So you can't cheat that way. It will still come and get you.
Yeah, I was just okay. So I guess it's just a natural thing to do, right? I mean, yeah.
And in fact, I mean, what we ended up using was Haar measure for the unitary group, for the SUN group. And I'm sure someone cleverer than me could say, well, naturally it has to be Haar measure. But in some sense, what we did was we started with Haar measure on the unitary case and then looked in the sort of the special, zero measure subset, but kind of rotate things around to have just that sub. Yeah, so the subgroup SUN from UN with Haar measure turns out to be SUN with Haar measure.
Okay, so I guess one last question is, in the end, what you did was you took some random interval of, let's say, of size 2 pi over n.
Yeah.
And then you counted what's the probability of it have only one eigenvalue there, right? And
yeah.
So at the end did not depend on the position of the interval, because, right?
That is a good question. Yes. And no, it doesn't.
Still, the question is still about some special sorts of intervals, right?
Yes. So the interval is placed on the Gram intervals. These, in the unitary matrix, they're the equidistributed things. It doesn't matter which one of those you choose. So we did manage to prove that this Gram interval is the same as this Gram interval, but it is important that it's a Gram interval because the statistics change as they must, because otherwise you'd end up with on the nose equal to the unitary case. So it's important it was a Gram interval. It doesn't matter which one it was.
Should be something between pi over j pi over n, and then so I guess my mind is at ease now. Okay, that was great. It was very nice talk. Thank you, Chris.
Thank you very much.
Let's another round of applause for Chris and for his answers to the many questions. Sam, did you want to say something, or just open the mic for applause?
I just